Assalamu alaikum everyone. This is lecture 3 on nonlinear control system. We are following the book Applied Nonlinear Control by Slotting Lee. This book, we are actually covering the chapter 2 of this book. So the topic that we are covering is the phase plane analysis. In the last class, we have seen how to plot the phase plane analysis of a first order system. In this class, we'll be trying to cover the second order system. I'm not sure how far we can cover, but let's begin at least. Then we'll see how far we can go. So before going to the phase plane analysis, one topic can be discussed, that is the symmetry in the phase plane portraits or phase portraits. Symmetry in phase portrait. Okay, so actually if you have symmetrical properties, symmetrical about x1 axis or symmetrical about y2 axis, or symmetrical about the origin in both x and y axis. So in this case, the analysis and the plotting becomes a lot easier, like if it is symmetrical about x1 axis. So far, if you can recall, our x1 is basically what we generally refer as x-axis, and x2 is what we generally refer as y-axis, and x1 and x2, both of them are actually phase variable. So if our system is symmetrical about x1 axis, okay, in that case, or x2 axis, in that case, if we just take half of the plot, if we just can have half of the phase portrait, then actually we can have the whole picture. And if it is symmetrical about both the axes, okay, so both x1 axis as well as x2 axis, in that case, a quarter of the phase portrait will give you actually the full picture. So that is why it's better actually to go for the symmetrical properties if possible. So for the symmetrical properties, we can take the equation x double dot plus f x comma x dot equal to 0. So nothing to be worried about, as I already said that this is nothing but x double dot plus x dot plus x equal to 0. There may be some constant a, b, c can be here. So a pure second order system basically. We haven't yet discussed the nonlinear phenomena in the phase plane analysis, but we'll go into that. Before going to that, let's study the linear system, how it works, and then we'll be trying to go for the nonlinear system. Now here in this system, if we take x1 equal to x, okay, then now we get that x1 dot will be actually x2, okay, in turn it is actually x dot as well, same thing, and then x2 dot will be actually your minus, this quantity minus f x1 x2. Okay, so this is your this is just a side note, but this is your actually state equation. So those who are not familiar with this state equation, I will advise them to actually cover the chapter 3 of the Norman S. Nice's Control System Engineering book. Okay, so that then how from transfer function to go to the state equation or state space representation, or from state space representation to the transfer function representation, so that thing will be clear. So in some advanced, in most of the advanced courses, Basically, we go for the state space representation, especially in this course. So it will be a prerequisite actually to know. So most of you are already, I think in undergraduate level I have covered. So for some of you, if it is not covered, so I'll advise them to go to cover that topic from chapter 3 of Control System Engineering book. That is the author Norman S. Nice. Okay, so now here we have the system. So and which is also this is nothing but dx1 by dt, and this is nothing but dx2 by dt. Okay, so basically symmetry is also referred to the equation as well. So if we can find out the slope equation, so that is dx1, if you just divide dx2 by dx1, this equation, then we can find out the slope of it, and which will be minus fx1 x2 divided by x dot, or x1 dot x1 dot, because it is actually x2, so x2 can be represented by x dot as well. So bottom line is they will also have a symmetry about the slope of the equation. So it is better if you can find out the symmetry, and the condition for symmetry about the x1 axis is symmetry about x1 axis, condition for that, which is generally our x-axis. The condition for that is f x1 x2 should be equal to f x1 minus x2. Okay. Then if it is the symmetry about the x2 axis, which is y-axis, symmetry about x2 axis, then the formula is f x1 x2 should be equal to minus f x1 minus x1 x2. Okay, so if these properties match, then there will be symmetrical about x and y axis, and because of which this half of the plot should be enough to finish the complete portrait. Now, if it is symmetrical about the origin, then symmetry about the origin. So in that case, f x1 x2 should be equal to minus f minus x1 minus x2. Okay, so this is all about the symmetrical thing, and if it is available, in that case you just have to plot either half or quarter of the figure. That should be okay. Now, before going into the phase portrait of the second order system, one important thing that we should review is the eigenvector and the eigenvalue. So let us try to review that. Start with the eigenvector. Okay, so this is the definition. What it means is that if you have a matrix A, and if you have a vector xi. So both of them, if you multiply those two, then it will have some constant value lambda I into xi. Okay, so this is where lambda is just a constant, just constant. Okay, so it can have multiple, so constants maybe. So if this equation is followed, then we can call that xi is the eigenvector of the matrix A. Okay, so what actually it represents, what it means is also very important to understand. That is, if you have a matrix xi, okay, and you multiply this one with a matrix A, okay, so and these two has to be collinear. That means they have to be on the same line. If they're on the same line, then actually xi is a eigenvector of the matrix A. So graphically, this is what it means. So if you have a matrix xi, this is your vector xi, and if you multiply with the matrix A, then it is somewhere here is your axi. They are not collinear, so basically this particular xi is not a eigenvector of matrix A. But if you have something like this, uh, this is your matrix X, I, and if you multiply, it can be reduced or it can be more. So then we call this one as a, this Xi is a actually eigenvector of the matrix A. Okay, so let us put some arbitrary examples. Say that A is having a value something like this, 3, 0, 1, 2, and we are just arbitrarily taking one vector, that is x equal to 1, 1, arbitrary choice. Now we want to be sure that with this value of x, whether it is a eigenvector of this matrix A or not. So for that, we have to simply multiply those two. Then let's see what we get. 3, 0, 1, 3. Sorry, 1, 2, and 1, 1. So if you just multiply, it is 3, and then you have 1 plus 2, that is basically 3, 3, and you can take the common factor is 3, so what do you have? 1, 1. So basically this is your 3 times x. So basically use your lambda x. Okay, so lambda value is 3 here. Okay, so as you can see, after multiplication, actually we have a, after the multiplication with the matrix to the vector, we get the vector with some linear multiplication of the vector. So graphically what it means, graphically, if you try to plot it, graphically what it means is your 1, 1 is your, say, vector x, this one is your x, now x, and now if you multiply a and x, then you're going to 3 and 3, so somewhere here. So basically somewhere here. So now this is your Ax, and this is collinear to your matrix X. So we can say that this particular value of X is actually a eigenvector. Okay, so this is what is the meaning of the eigenvector. Next, then what we have is eigenvalue. So eigenvalue or eigenvalues of a matrix. Let us write the definition first. Eigenvalues of a matrix A are the values of lambda I that satisfy that equation A x equal to lambda x. okay, for x is not 0. So x is 0, then this equation will always satisfy. So the condition is xi. You can also put I here, xi, arbitrary value. Okay. So the values of lambda, those actually for which this equation is valid, those values are actually known as eigenvalues. Now, how to find out the eigenvectors? To find out the eigenvectors, actually we have to find out the eigenvalue as well. So starting from this equation, you can take the parameters into the other side. So we have 0 equal to lambda xi minus axi. Now take common of the xi, so lambda identity matrix will be left here. Okay, so minus xi. Okay, so if we solve for xi, because they're all these are also zero matrix, because if you take it to the other side, then zero vector will be also there, zero vector. So now if you solve for xi, then actually you have to multiply both sides of this equation by lambda I minus A inverse. Okay, so if we do that, then what we have is xi equal to lambda I minus A inverse with 0 is a matrix as well, null matrix, null vector. So now we know that inverse matrix can be written as adjacent of lambda I minus A divided by the determinant of lambda I minus A. Okay, so then we have 0 null vector as well. Now, what we have is a condition that we should fulfill is that xi cannot be 0. So xi cannot be 0. So if this is the case, then only possibility is we have 0 by 0 that will give you some valid solution. Otherwise, all the solution will be actually x equal to 0. So 0 by 0 is undetermined. That means some value is possible, something we don't know maybe. So how 0 by 0 is obtainable? Only if the determinant of lambda I minus A is becoming 0. Then we have 0 by 0. Then actually we can have some undetermined value, which is not 0, of course. Now, so the condition that we are obtaining from there is determinant of lambda I minus A has to be equal to 0. Okay, so this is how from this switch we can actually find out the value of the eigenvalues, and once we got the eigenvalues, we can easily find out the values of the eigenvector as well. So let us see one example. Say a system matrix is being provided. A system matrix is being provided A, and the value of the A is given. This is also from Norman S. Nice's book. I'm just reviewing the topic. I think it is under the article 5.8 minus 3. So this is what we have, the matrix A. So for this particular matrix, we need to find out the vector. So first thing to find out the vector is to find out the eigenvalue as well. So basically, determinant of lambda I minus A. This is what we have to do. Okay, so now what we have is lambda will be multiplied with the identity matrix, and the matrix A is also of the order of 2. So we can have something like this, lambda multiplied by 1 0 0 1. So basically lambda 0 0 lambda minus the matrix is minus 3 1 1 minus 3. Good. Then what we have here is determinant of, if we subtract that, lambda plus 3, then minus 1, lambda plus 3. Now if we input value, lambda plus 3 whole square minus 1. So basically lambda square 6 lambda plus 9 minus 1. So basically lambda square plus 6 lambda plus 8. We subtracted 1 from 9. So this is the value we get. So values of the lambda we can get is can be written as lambda plus 2 into lambda plus 4. So eventually that will give us lambda equal to minus 2 and lambda equal to minus 4. These are the two eigenvalues. Now, once we have the eigenvalues, now next thing we have to go is to find out the eigenvector. So we know the condition for the eigenvector is A times x. A times x should be equal to lambda I times x. So you already know a that is minus 3, 1, 1, minus 3, and x, since it is a matrix of 2, square matrix of 2 into 2, then 2 by 2 matrix, so actually it has to be of order 2 as well. So this will be x1 and this will be x2. Okay, so then lambda, say we are doing it for the first one. So say we are doing it for minus 2. So put the value of the lambda as minus 2, then again x1, x2. So from this one, we can actually find out the two equation. Minus 3x1 plus x2 equal to minus 2x1. Okay, and minus, x1 minus 3x2 equal to minus 2x2. So you solve it, both of them will be giving you the same solution in most cases. So basically that is x1 equal to x2. Okay, so both the quantity is equal. So it actually means that any parameter that you have where your x1 is equal to x2 can be an eigen vector. So say our vector xi or x can be written as c and c constant values, any values, though they're equal. So say one simple one is both the magnitude is 1. So 1 is also the eigenvector. Similarly, it can be 2 to any equal magnitude, it can be 3. Okay, so this is one of the eigenvalues. So this is called your x1, this is x2, x3. So any eigenvector that you want, can number of eigenvectors possible. Similarly, now if you take lambda equal to minus 4, so lambda equal to minus 4, in that case again minus 3, 1, 1 minus 3, x1, x2 gives us minus 4, x1, x2. Okay, so now now, if you find out the equations again, minus 3x1 plus x2 equal to minus 4x1, and x1 minus 3x2 equal to minus 4x2. So they will also give the same equation, the same relation, that is x2 equal to minus x1. So what we can find, the eigenvector will be something like this. I equal to c and minus c, any constant. So if the c is 1, then we can have 1 minus 1 or 2 minus 2. So something like this. This is how they have infinite number of eigenvectors possible for this system matrix A. Okay, so this is the review of your eigenvalue and the eigenvector, which is, I believe, a bit simpler. And now let us try to plot one phase portrait. One of the method, let us start with one of the method, and after that we'll be going to few other method, maybe if time is available in this class or in the next class. So say we are giving a question. The question is, question says that draw the phase portrait of the system represented by the following equation. Say we have given two equation, x1 x dot equal to 4x minus 3y and y dot equal to 6x. Okay, so 6x minus 7y. So these two are two equations given. So now based on these two state equation, so it can be any value like x1, x2 or xy. So it doesn't make a difference. It only represents the state quantity. So y is a quantity here and x is a quantity here, something like this. So apart from that, nothing is that complicated. So this two equation is provided, and x and y are the state variables, and we have to draw the phase portrait for this particular system. So how to find out the phase portrait? The simple idea is we will go in step by step. The first step here, step one, here is step one, is finding the critical or equivalent points. Okay, finding critical or equivalent points. Finding critical, yeah, sometimes it's been called critical, sometimes it is called equilibrium, or also singular. I think in the last class we have said singular point or equilibrium point. So this is step one. So for finding the equilibrium point, the definition we already said that singular point is the point where the system states can stay forever. That means there is no variation available. That means your two changing parameter with time, like dx by dt or dy by dt. These two parameter will not be available, and because of which the system will be always in the state where they are. So the condition that we have to apply is x dot equal to 0 as well as y dot equal to 0. So that will give us the equilibrium point. So what, from this equation, you can say that 4x minus 3y should be equal to 0 and 6x minus 7y should be equal to 0. And now if you try to solve this one, we will be finding only one solution that can satisfy both the equation is x equal to 0 and y equal to 0. So 0, 0 is actually the equilibrium point for this particular problem. So this is the first step, finding the equilibrium point. The second step is to finding the eigenvalues. Okay, so step 2 is finding the eigenvalues. Step 2. Finding eigenvalues. Okay, so for that we have to find out the system matrix. Basically, system matrix is already been available in this equation. So basically, we can write this equation as x dot y dot equal to 4 minus 3, 6 minus 7 into x and y. Okay, so basically this is our system matrix A. So the property that we have to follow to find out the eigenvector is basically determinant of lambda I minus A has to be equal to 0. So we know lambda I is basically lambda 0, 0, lambda identity, just multiplying with the identity matrix. Then we have the system matrix, that is 4 minus 3, 6 minus 7. Okay, so then we have to find out the determinant of this, and this the magnitude of it should be equal to 0. Okay, so what we find is lambda minus 4, 3, then we have minus 6, then lambda plus 7. So it should be equal to 0, then lambda minus 4 into lambda plus 7 plus 18 should be equal to 0. So now if we simplify a bit, then what we are going to get is lambda square plus 3 lambda plus 3 lambda minus 10 because there will be minus 28, so minus 10 should be equal to 0. Now if we try to find out the roots of this one, then lambda square plus 5 lambda minus 2 lambda minus 10 equal to 0. So take common, I'm sorry, I'm doing just very basic things. 2, then we have lambda plus 5 equal to 0. Okay, so lambda plus 5, lambda minus 2 equal to 0. We can find two conditions, two lambda values, that is minus 5 and plus 2. So one of the eigenvalue is positive and the other one is negative. If you can recall, these eigenvalues are actually nothing but the system poles. So poles, if the magnitude of the pole is plus, then it will give you exponential growth. And if the magnitude of the pole is negative, then actually it will give exponential decay. So as you can see, one of them has exponential increase and one of them has exponential decrease. Now, the system, the phase portrait or the trajectory that we are drawing, it is actually subjected to the initial condition. So in some initial condition, it may converge, in some initial condition, it may diverge. So this is what we want to figure out from the phase portrait, and we have to explain or understand what is actually happening. So now next state 3 is to figure out the Eigenvec vector. Step 3, finding the eigenvector, finding the eigenvectors. Okay, so formula again, the same formula, that ax should be equal to lambda x. So here lambda equal to 4 minus 3, 6 minus 7, and you have x and y. X and y equal to minus, if we take the minus 5, then okay, sorry for the interruption. Now we're taking the first one, that is lambda equal to minus 5. So x and y is our phase variable, not like the previous one where we have x1 or x2. So it can be any value, as I already said. So now if you can find out the two equation. So basically for x minus 3, y should be equal to minus 5x. Okay, and 6x minus 7, y should be equal to minus 5y. Okay, so now if you try to solve this one, so what you're going to get is, if you take both in the same side, 9x should be equal to 3y. Okay. Okay, so you can divide it by 3. So actually, y can be equal to 3x. This is one equation. And basically, if you do the other one, it will also give you the same thing. So both of them actually gives the same result. So basically, if we get x equal to 1, then the y will be actually 3. So this is how you have to find out the matrix for this one. Okay, so let us assume that x equal to 1, then y equal to 3, and then your matrix or the eigenvector is becoming something like 1, 3. Okay, so this is one. Similarly, for the other eigenvector that we have, that is lambda equal to plus 2. For that also you have to apply the similar idea, and that is 4 minus 3, 6 minus 7 into xy equal to 2 into xy. Okay, so again, the equations that we are going to get is 4x minus 3y equal to 2x, and 6x minus 7y equal to 2y. So both of them eventually will give same equation, that is it will be basically 2x equal to 3y, so 3y equal to 2x, or simply y equal to 2 by 3x. So we can choose any value of x, but so that we can have a very smooth equation, we can choose the value of x to be 3, and then y will be actually 3 getting cancelled out, y will be 2. Okay, so for this particular case, with the eigenvalue of 2 plus 2, we are getting a matrix, we are getting an eigenvector that is actually 3, 2. Okay, so this is the plot of finding the eigenvectors. That was actually step 3. And finally, we have step 4 is basically plotting. Step 4. So one thing we know, we already figured out, is that for lambda equal to minus 5, we have x which is 1, 3. 1, 3. Okay, and for lambda equal to 2, we have a vector that is 3, 2. Okay, so you can use both the equation, like the one that we have figured out, y equal to 3x, or even this vector to plot the line. Similarly, y equal to 2 by 3x. You can also use this equation or this one, whatever you prefer. So it's up to you. Yeah, okay, now in the phase plane, which is in this case yx or xy plane, so here you have to find out these two equations for these two cases. But one thing you have to remember, that minus 5 is a pole of the system that is on the left half plane, and it will give a decaying nature. So basically the line will be actually converging towards the equilibrium point. In our case, the equilibrium point we also calculated is 0, 0. So this one will be converging towards 0, 0. While since because you have a positive here, so this one will be diverging from 0 or at the equilibrium point because it will give you exponential growth. So if you try to find out the solution, it will have something like e to the power twice t plus, so it will have exponential growth, and this one will have a solution e to the power minus 5t, and that will have a exponential decay, and because of which this one actually converges and this one actually diverges. Okay, so let us plot the equation first, then we'll see what is happening. So okay, so now this is our axis. We are calling this one as x-axis, and we are calling this one as a y-axis. Now the first one is actually 1, 3. So 1, 3. We are somewhere here, and the second one is actually we have 3, then 2. We are here. Okay, so let us take the help of the ruler. So ruler will actually, the scale will actually help us to plot it. Now once you have these 2 points, you have to just join the origin with these points, and then you have to extend the lines. So okay, so this is what we have. So let us use a different color, it will be better to illustrate them. Okay, and the other one. So one thing we have to be careful about the phase portrait is there is no time is not present here in your phase plane analysis. What we are doing is we are plotting one phase with respect to the other one. Okay, so now we are drawing the 2, 3, 1, that is for the lambda 2, lambda equal to 2. So now this one is for lambda equal to 2, and which will have a exponential nature e to the power twice t, something like this, because of which it will diverge from the equilibrium point. This is our equilibrium point. Okay, so 0, 0. So in both the direction it will actually diverge. And what about the other one? This is for lambda equal to minus 5, and because of which it will be actually e to the power minus 5t. So it will actually converge towards the origin. So you'll have something like this. Okay. Now this is only for these 2 cases. Now in these 2 cases, what you can figure out is that once your system is on the red line, so your system will be stable. It will be always converging to the equilibrium point. The bottom line is we call it equilibrium point 0, 0. So once the system is at that particular point 0, 0, it will always be there. So it will not come out of it. So this is your equilibrium point. So we are interested about a small perturbation somehow about the origin. So what will happen then? So if you have a small perturbation along this axis, along the red axis, you are somewhere here. So again, it will come back to the same point. Again, if you have some perturbation, you are here. So again, it will go back to the origin. Okay. But if you have some perturbation along this purple line, so now you're here, so you'll not come back to the origin, rather the direction of here is this, so you'll actually diverge away. So similarly, so if you're somewhere here, so your system will be diverging away. So as we said, the nonlinear systems are actually subjected to the initial conditions as well. So this is how in one direction the systems behave. If we start from somewhere with your initial conditions somewhere here, so you are going to a stable system. But if your system is somewhere here, so it will be actually diverging away. So your system is not a stable one. Now, after plotting, what about the other initial conditions? Say one system is having initial condition here. What will happen to it? So basically, rest of the initial condition, apart from these two lines, will be following this same trajectory like this. Okay, so they'll follow like this. So if something is starting from here, they'll come here and go there. And similarly, if something is starting here, it will be following the arrows around this line. Okay. And similarly, in between this red and the purple, the top one, you'll have some system starting. So you'll be going through this path, something like this, the following the arrows. And likewise in the downwards as well, following the arrow. Okay, so this is your system trajectory. So subjected to your initial condition, where your system is landing, this has been actually determined by based on those vectors, and the rest of them would be actually exactly following the directions that we obtained. Okay, so this is the easy four-step procedure actually to find out the phase portrait of a second-order system. We are not still talking about nonlinear, rather we are discussing only the linear portion. Okay, so after plotting it, you should be analyzing the way how it is actually happening. So let us, to make things clear, let us go with another example. So we have a system something like this: x dot equal to minus 2x plus y, and y dot equal to minus 4x. So this is what we have. Now the step one, this time we'll be trying to make it a bit quick. So in this particular example, the step one is finding the equilibrium point, or basically the critical point. So in this equilibrium point, again, the condition is same: x dot equal to 0, y dot equal to 0, and that gives us x equal to 0 as well as y equal to 0. Okay, so same equilibrium point, x equal to 0 and y equal to 0. Next is the eigenvalue. So let us go for eigenvalue. Before that, let us find out the matrix: minus 2, 1, minus 4, 0. So this is your matrix A. And now for the eigenvalues, del determinant of lambda I minus A. So we have minus 2, minus 4, 1, 0, and sorry. We have to find out the del 0, 0, sorry, lambda 0, 0, lambda minus 2, minus 4, 1, 0. Okay. Now, if you just find out the determinant of it, then what we are going to get is lambda plus 2 minus 1 plus 4 and lambda. Okay, now lambda square plus twice lambda minus plus 4. So and this should be equal to 0. So basically lambda 1, 2 can be figured out as minus b plus minus b square root over b square minus 4ac. So minus 2 plus minus 2 square minus 4 into a into c divided by twice a. So it will be 2 by 2. So 2 by 2 is basically minus 1. minus 1, then you have plus minus 4 minus 16. So basically minus 12. So because of the minus, we'll have j, and then we have root over 12 by 2. So 12 by 2 can also write as 4 into 3. So basically 2 can be cancel out. So what will be left is minus 1 plus minus j root over 3. So now in this case, you have a eigenvalue that has real quantity or as well as have imaginary quantities. So real quantity is actually negative. So as we know that the real quantity actually determines the system's behavior in terms of exponential growth or decay. So if the real parameter is negative, so it means actually exponential decay. So exponential decay, and it is also in phase plane. Exponential decay actually represents as a convergence towards the equilibrium point. Okay. And what about the imaginary portion? As you know that imaginary portion actually represents an oscillation, and is in phase plane. Oscillation is basically represented by a rotation. Oscillation. Okay. So in the phase plane, this is actually represented by a rotation. By a rotation. Okay, so what we have something like this. So we'll have a decreasing rotation, so around the equilibrium point. Okay, so what should be the direction of the equilibrium point? So for doing that, actually, whether the direction should be clockwise or anti-clockwise, to find out the direction, you have to, a random value has to be chosen in the phase plane, and it can be 0, 1 or 1, 0, okay? And then it has to be multiplied with the system matrix A, and whatever the transformation we are having, then we have to figure out which direction it is actually going. I think you are getting confused, but don't get confused. Let us explain with example, so then it will be a lot easier. So say our system matrix here, our system matrix here is minus 2, minus 2, 1, and minus 4, 0. So let's say minus 2, 1, minus 4, 0. So we'll be choosing any point in the axis. Say we have this. Okay, so maybe yx or x1, x2, whatever. So we are taking any arbitrary value, say 0, 1. So you're taking this value. Okay, so we are taking 0, 1, and we are multiplying with this one with our system matrix. This is A, and this is arbitrarily taken point. So after multiplication, let's see what the value we are getting. So basically this will be 1, 0, 1, and then you have 0, 0. Okay. So this is the point we are getting. So what we are going to find is 1, 0. So basically we are getting here. So we will have a direction something like this. Okay, so what does it mean? We have a clockwise direction. Okay, so this is how we have to find out the direction. So bottom line is it will have a rotation, decreasing rotation, and the magnitude of which is being obtained, the direction of which is obtained by choosing any arbitrary point on the plane, and then you transform it using the system matrix and to see in which direction it is going. So after that, now what should be our solution of this particular case? So the solution for this particular case will be we have an exponential decrease and also we have an oscillation. So basically we will have something like this. So, and the direction of the rotation is, according to this diagram, it is actually clockwise. So we'll have something like this. Okay, it wasn't that small, but eventually this is how it will look like. Okay, so a decreasing oscillation, decreasing rotation, and which is clockwise. So this is the phase portrait of this particular system, which has a negative real part as well as oscillation. Similarly, say, let us discuss few example, like if you have something like this, lambda value is something like this, lambda equal to 3 plus minus j over 6, something like this. So what does it mean? So first of all, this is plus, and because of which it is divergent. Divergence will be experienced, and as well as because of this you will have oscillation or rotation. Okay, so rotation, what does it mean? And also in this particular case we will have that system matrix. So if we don't have system matrix, we're going to find out the direction of the rotation, but we're just assuming that what will happen is starting from the origin, gradually actually it will be spiral out. So this will be your increasing direction. Okay, so this will be the corresponding phase portrait. Now this is case one, and the other case possible is say lambda only have oscillation. Lambda value is only pure uh, imaginary. So in that case, what will happen? So there is no real part, neither increasing or decreasing. So it means actually it will give you pure oscillation, and pure oscillation is a circular motion around your equilibrium point. So basically, even though my one was not properly drawn circle, but again, so all of them will be actually centering the equilibrium point. You will have circles centering the equilibrium points. Now, whether it will be clockwise or anti-clockwise, we have to again multiply with that system matrix with any arbitrary chosen point. So this is may or may not be clockwise always. It can also be anti-clockwise at times. Okay, so but what is the system's stability analysis? What the stability point from Stokes point of view, what we can conclude is that definitely this one, since it is converging to the origin, so this is stable system. And since this is diverging from the equilibrium point, this is unstable. Okay, and for this one, we can say that it is neither converging nor diverging, rather it is, we can call it maybe marginally stable. Okay, so it's based on lambda values basically. So there are very few other lambda values possible, and how their responses are going to look like. So all these things actually we'll be discussing as well in the next class that we're going to cover. So basically two things are actually left. What we covered is actually complex pole. Complex pole we already covered. This is one thing. The pure imaginary also covered. Imaginary. Okay, so 1 plus 1 minus is covered, 1 positive and 1 negative is covered. Now what is left is basically both positive and both negative. Those two cases are not covered. Both positive and both negative. Okay, so this one is left. So we can actually go with one example of that one as well. But it is almost, I think, 1 hour. So uh, I think again we have limitation of time, so it will not be. We can just arbitrarily say that we have something like this. We're not solving it, rather I'm letting it up to you, but arbitrarily let's also discuss this thing. Say you have lambda equal to 2 and lambda equal to 4. So based on that, say we have one curve like this. Say there we have one line eigenvector, and this is another eigenvector, say arbitrarily. Okay, so just say that this is for lambda equal to 2 and this is for lambda equal to 4. And this is your, say, x is y and this is x. So now what should be the pattern? Now, first thing we should know is that lambda is plus in both the cases. So there is no question about the direction. The direction will be always diverging. Okay, so always diverging. Now, this is your equilibrium point. So what will happen in the rest of the cases? So that is what we actually are interested to know. So since the solution for this one will be e to the power 4t, the solution for this one will be e to the power twice t, and as t is approaching infinity, so e to the power 4t will be way more higher than e to the power twice t. So basically at the very beginning it uh, may start from the smaller one, but eventually it will go back and parallel to the asymptote of the higher one. Okay, similar thing here. It may start from, this should be the direction diverging of force, so this is the direction. Similarly, it may start initially behave like the smaller one. Eventually it will be like the asymptotically following the higher one. So this is the phase portrait if both of them are positive. Similarly, we can also briefly discuss, even though we are not going with examples, I am letting you to actually go with this example. So now what will happen to this one? With both of them are negative. So similar figure we can actually draw. Say, okay, systems proper stability wise, it is always diverging. So it is actually unstable, no question about it. And what about say two figure we are drawing, two eigenvalues. Again, similar pattern. Say this is y, this is your x, and this is for lambda equal to minus 2, and this is lambda equal to minus 3. So as we know that lambda equal to minus 3t will be disappearing quicker compared to minus twice t. So now the smaller is actually minus 3 and bigger is minus 2. So initially it will start, again all of them are actually converging because of the minus sign. So it will come initially actually they will start from the same location. Okay, so which one? Initially, it will follow the smaller one, and while it is approaching, then it will be actually following the larger one. So coming back, initially it will be following the smaller one. So it will go something like this, the smaller one, and then finally it will be actually approaching similar to the larger one. So you'll have something like this. Similarly, you will have I think that it would have been better to draw with a different color, but initially it will be with lambda equal to 2 parallel to that, and finally whenever it will be approaching, it will be approaching so like your other one. So bottom line is all wherever it is starting, it doesn't make any difference. It is always starting, it is always reaching to the equilibrium point. So in this case, we can say that this is actually a stable system. So wherever you start, eventually whether it is starting similar to the smaller one, then approaching towards the uh, bigger one. In negative numbers, minus 3 is actually smaller than minus 2. So this is how the system will be looking like. Okay. Sometimes we can also have some other combination like this. Unstable ones can directly, instead of having these directions, you can have directly coming out something like this, always going out, diverging. Okay, so this is also possible. And sometimes for some stable system, it is also possible to have something like this, always see like a star combination, always coming towards converging towards the point. So this is also two examples of stable and unstable scenario. And sometimes we can also have equal values. So in the equal values, if both of them positive, then they will be actually uh, diverging, and if both of them are negative, then it will be actually converging, equal magnitude. So similar diagram that we have drawn, we can also draw pictures like this for equal magnitude as well. But in this case, you will have only one a vector, not two, because both of them are actually providing the same eigenvalue. So you'll have only one vector. So I think I can let this one as a homework for you. So how can you have repeated roots? Some of the examples maybe I will be trying to provide you to find solve by yourself. Okay, so some of the names that we actually haven't given is the one that is having both of them, that is also known as saddle point, like one of them is converging, one of them is diverging. So one converging, one diverging, that node is known as saddle case, saddle point. Okay, so in one direction that is stable, and in other direction it is unstable. Okay, so this is what we initial idea of all the cases that we have considered is also linear. So this is one of the way actually to plot the phase portrait. We'll also see the analytical methods as well as isoclean. There is another method in the book, isoclean. So that will also be covered inshallah in the next class. See you in the next class, inshallah.